All right, so today's the first of the 3 reviews. Tomorrow will be 6 p.m. as well, and then Friday make it a little earlier because I don't want to ruin you guys' night with this stuff. It's going to be at 5, all in the same place, K228. All right, so I'm Pat. For those of you who don't know me, SIGEP, woo, whatever. DiffyQ. We're going to go over two main things today. The 2 things that were not even covered in any of the exams, which are Fourier series, the sine and cosine series, which are types of Fourier series I got 2, and partial differential equations, which are a pain in the ass to do. They are long. They're going to be like 45 minutes each. There's only going to be 1 on your final. It's going to be a large percentage of your final, so it's good that you know it. It's all it is. Don't get sad about it yet. It's going to be. It's just a bunch of steps, just like everything else in DiffyQ. It's a bunch of steps. You memorize these steps, you are going to get it right. So that's the heat or wave equation. It's another thing they call it. Both are, you might hear your professor say, oh, the heat equation is going to be on, the wave equation is not, or whatever. They're both the same kind of method to solving it. So don't get freaked out from that. All right, so without further ado, let's get started. And by the way, SITV, I'm on that thing. SITTV, I don't even know what it is, but I'm on it. So thanks, guys. All right, so first one we're going to start with is the Fourier sine series. So the Fourier sine series is just, there's 2 things for each of these series they have to memorize. Both of them are very similar. And then other than that, it's just getting a bunch of terms and writing them out. So Fourier sine series. All right, what that is the function itself, so like the answer of whatever, like you know how I always say there's a template of your answer, and you have to put in either constants or different functions into that template to get your answer. So what I'm going to write here is the answer of your Fourier series for however many terms you need it for your Fourier sine series. So it's going to be the sum from n equals 1 to infinity of a constant an times the sine of n pi x over L. And L is just the length of the function because it can go from 0 to pi, 0 to 2 pi. You guys will see that in the example. So this is important to know. It's fairly easy to know. So it's good that you know that. All right, and then what we're doing in this Fourier series problems is we're going to get a problem. On the final, it's going to be find the first 5 or 4 non-zero terms of the Fourier cosine series or Fourier sine series of x function, of f of x, whatever that's going to be. So what you do is, you know this is going to look like the answer. What you need to do is find n, and you need to find a of n, your constant an. So whether it be a1, a2, a3, a4, or whatever that are non-zero constants. So what this constant is equal to, I'll write that right here, an is equal to 2 over L times the integral, and yes, you have to do integrals now, 0 to L of f of x times the sine of n pi x over L dx. So it looks very similar to the answer, but this is just to find the constant. So your constant equals all that stuff. So okay, any questions on that? Anybody at all throughout the review have any questions at all, please just stop me and ask. Yep.
You're assuming it's even right there, right?
I'm assuming.
Because isn't it negative L to L?
Yes. Yeah, but on the test, it's, so this would be, the real function is, you're right, the real constant is going to be 1 over L from negative L to L. But since you're assuming it's even in these kind of problems, and on the final you assume it's even, it's going to be from 0 to L and then 2L. So you're going to have a function like, I don't know, this, right? This is even. It flips around the y. So if you go from negative L to L, that's the same thing as going from 0 to L, since it's the same here as it is here, and doubling it. So you just assume it's even. All right. So we're going to do an example with that. All right. So your example is find the first 5 non-zero terms of Fourier sine series, and then of this function f of x, which is going to be a piecewise function most of the time. This is a very simple one. 0x less than pi pi less than x less than 2 pi. Okay, so that's your function. So we need to find the Fourier series of this. In the Fourier sine series, first 5 non-zero terms. Okay, so the first thing to do is we have our function. We know what the answer is going to look like, but we need to find the constants, a, n, 5 of them, that go into that function. Okay, so the first thing to do is we need to find our L value, right? So the entire L value is going to be, where does this whole function go from? It goes from 0 to 2 pi. So that means the length of the entire function is going to be 2 pi. So L is equal to 2 pi. So we can start writing this term, this an term, as 2 over 2 pi, so basically 1 over pi, integral from 0 to L, so 0 to 2 pi, of f of x, which right now we'll leave as f of x, because from 0 to 2 pi, there's 2 f of x's. The first one from 0 to pi is just 0, and the second one is 1 from pi to 2 pi. And then we have sine, what else we got? N pi x over L, which is 2 pi, dx. Okay, so since, like I just said, from 0 to 2 pi, there's two kind of domains. It switches to what it is. It goes from 0 and then up to 1. We're going to ignore the 0 part. So because the integral of that would be 0, because you're going to end up with, it's going to look like this, from 0 to pi, pi to 2 pi, like that. So the integral here is going to be obviously 0 because it's a line on the axis. And the integral here is what we're going to find. But it's all like weird Fourier engineering waves and stuff that you could project that. I don't know. I don't really know the theory behind any of this, but whatever. Okay, so we're going to ignore the 0 part because the integral of it's 0. So we're going to go straight to the second domain of this function, which is going to be where it equals 1, where that's pi to 2 pi. So does that make sense to everybody that we're skipping the first part because it's 0? Okay, good. All right, so we're going to still going to have 2 over 2 pi. We can just make that 1 over pi. And then we're going to go from 0. Nope, we're not going to go from 0. We're going to go from pi to 2 pi. And that's going to be, f of x is going to be 1 throughout that whole pi to 2 pi. Sine of n pi x over 2 pi. So that's just n pi x over 2 pi. We can make this, the pi's cancel out. Just make that, I'll just make it a little neater. So you have nx over 2, and then dx. All right. So now, yep, question.
Would there be any case where the first domain wouldn't be 0?
For cosine, it would. That's where we get to where the first domain starts out up here. Then we have a different, it's going to be a little different.
Okay.
Yeah, okay. Okay, good question. All right, so now we just do some calc 2, find some integral, calc 1, find some integrals. So wait, all right, I'm not going to put that there. All right, so the integral of sine, what is it? Negative cosine, right? I was about to ask you a question, but I'm like, eh. All right, so negative cosine. So negative cosine, put that in parentheses, of nx over 2. Can everybody see, by the way? Maybe this thing, I don't know. I hope you could see. Shit. Whatever. All right. All right. You have that. And then it's going to be divided by the derivative of the inside. So the derivative of the inside is going to be n over 2. So you just put n over 2 on the bottom. And we can simplify that. We're going to do that in a minute. And then this whole thing is going to be from pi to 2 pi. Wait, what? Oh, fire hazard. Yeah. The whole place burns down. It'll be on YouTube also. So we'll be famous. All right. So you have that integral. I'm going to erase this and then go in the middle so you guys can see what I'm doing. Bless you. All right, so you have this. We're going to simplify that. We're going to move that n over 2 up to the top. We're going to, since we're dividing by a fraction, we're going to flip it over, multiply it by the fraction on the outside. So you're going to have 2 over, I know math, 2 n pi. 2 over n pi, make that negative, times the cosine of nx over 2. All right, from pi to 2 pi. All right, we got that. So what do? We just plug them in because we already took the integral because we're so smart. All right, so plug in 2 pi. Well, we can factor this out. We'll have 2 over n pi. So cosine, you put in 2 pi there. you get, the 2's cancel out, it'll be n pi. So cosine n pi. And then you do minus, this part will still be here. And then you put in the pi, which would be cosine of n pi over 2. This is sloppy, I'm sorry. All right. So does this make sense to everybody? What I did there with the integrals? Okay. So now we're basically done because this whole thing equals an. This whole thing, well, not this part too, but simplified this part, is equal to the constant in terms of n that we're trying to find. So what is simply to find the first 5 non-zero terms of this Fourier series, we simply just put in n equals 0, starting at 0, even starting at 1, n equals 0, 1, 2, 3, 4, 5. See what doesn't equal 0, then those are the coefficients. So we start in, put in A0. So you put in A0, you get negative 2, 0. Oh, you can't do 0. OK. See? You see why I can't do 0? Because it ends on the bottom here. So you just start at 1 because you don't want it to be undefined. All right, 1. So negative 2 over pi. Put in 1 here. Cosine of pi is negative 1. Negative 1. Put in 1 here. Cosine of pi over 2 is 0. So you get that, which equals 2 over pi. I'll go. I know I'm like going that way and this way, but I'm going to go this way now. A2 equals, if you put in 2 to right here, you get negative 1 over pi times the cosine of 2 pi, which is just 1, minus the cosine of 2 over 2 pi, which is just pi, which would be negative 1. So it'll be 1 minus 1. That equals 0. So this is 0. A3. So we can't use A2. A2 is not, we're going to skip that one because we need non-zero terms. So A3. You want, I'm going to do 4. 4 non-zero terms, just save time. All right, because A3. So now we just plug in 3. I'll go a little faster. Negative 2 over 3. Yeah, I just changed it, whatever. OK, cosine of, well, we know what that is. Cosine of 3. What would I do? OK, yeah, good math, yes. Wait, yeah. 1 minus negative 1, 1 plus 1. OK, I know 1 plus 1. All right, so this would be equal to negative 2. Good, if you see me make a mistake, always correct me. All right, so good, we have A2. That's good. Maybe I should put it back to 5, whatever. Well, no, we'll leave it at 4. OK, so bear with me. So A3. A3, we plug in 3. We get negative 2 over 3 pi times cosine of 3 pi, which is negative 1. And then you have 3 over 2 pi, which is 0, minus 0, equals 2 over 3 pi. All right, one more term, A4. All right, so A4, you plug in 4, you get negative 2 over 4 pi, which is just negative 1 over 2 pi times, put in 4 pi to that, you get 1. And then minus, you put in 4 pi there, you get 2 pi, which is just 1 again. So 1 minus 1, now it's 0. OK, now I have to go to A5. We'll do A5 over here. So A5, you plug in 5, you get negative 2 over 5 pi times cosine of 5 pi, same as cosine of 1 pi, which is negative 1, and then cosine of 5 pi over 2, which is 0. So then this goes to negative 1. So you have A5 equals negative or positive 2 over 5 pi. All right. So we have all, that was boring, I know, but we have all of our constants. We're going to use A2. We use A1, A2, A3, not A4 because it equals 0, and A5. So our complete answer, which I left not on purpose, left a nice little space, f of x is going to equal, this is your answer template, like I said in the beginning. This is what we're going to write. So an, first thing we write is A1. A1 is 2 over pi. Sine of sine of n pi x over L. So n is 1, pi is just pi, x is just x, and L is 2 pi. We can simplify that whenever. We don't really care. And then you're going to add. Is there a question? OK, you good? All right, so then plus A2. A2 is going to be minus 2 over pi times the sine of n, which is 2, pi over 2 pi. So that will go away, of x times x, bless you. And then we're going to have another term, which is going to be A3. That's going to be plus 2 over 3 pi sine of, what do we have? We have 3, because it's A3, so we have 3 pi x over 2 pi. And then you're going to add another term because you have A5 plus 2 over 5 pi sine of 5 pi over 2 pi x. All right, and that's your answer. All right, I know that was boring. It's going to get more interesting later, I promise. Is there any questions on that? Yeah? No? All right, I'll give you a minute to copy that down. Should I do one with cosine? Yeah? Okay. Okay. It's boring. I don't know, it's boring. I can't wait till we do PDEs. They're so interesting. And like they're so, yeah, but I'll do one. Fine. Okay. So did everybody copy this? Okay, I should have wrote it on the board that goes up, but I didn't. All right. Going away. All right. Ooh. I hit the gym too much. All right. Cosine series, very similar. Same kind of deal. I mean, I'm going to write down the stuff, but I'll write down the stuff. Let's see. So Fourier cosine. You guys hanging in there? I feel like I'm being boring already. Yeah, all right. No, it's you got to make it fun. You got to be excited. All right, so now we're going to use b's because we're dealing with cosines. N equals 1 to infinity. Okay, so Fourier cosine, it's very similar to Fourier sine. It's basically the same on this part. The only thing that's different is this term. The reason why this term is here is because cosines, where do they start at when you have a cosine? It starts up here. So you need to have a constant that initially puts it up. So why is it initially be up? Because we're dealing with usually straight lines and a thing. I don't know. But it's up there, so there's a constant in the front. Whatever. There's one more thing you have to know. So we need to, just like how we need to find all these constants for x of whatever many non-zero terms we're looking for, we also need to find b0. And the way you do that is b0 equals 1 over L integral from 0 to L of f of x dx. Okay, wait. Jake, was this 2 over L now?
The reason why it's 1 over L is because you don't have b0 over 2. So the way you have it works.
Okay, cool. Because we were arguing about that before. But okay, so that works. And yeah, and Jake's smarter than me, so I didn't know what to do. All right, so now same thing for bn. For any other coefficient that's not b0, we're going to have bn. It's going to look exactly the same. So 2 over L integral from 0 to L of f of x cosine of n pi x over L dx. All right. So that's the things you need to know. So that one and the sine one are the things that you need to look at, make sure you have memorized. Not going to be given to you. But then once you have this memorized, that's the hard part, I think. Because just doing the process finding the integral is pretty easy, I think. Okay, so let's get an example on this. Pretty sure I have one. All right, here we go. So our example is going to be the same thing. Find first, let's do 3. 3 terms, non-zero. I can't write in complete sentences. Non-zero, 3, whatever. You know what I'm saying. 3 terms non-zero, cosine I'll just jumble the words. Cosine Fourier series. I'll put the period right there. That's good. Yeah. Right? And then I'll do how many? Just all right. So right? All right. So f of x. F of x is just simply going to be x, right? So we're not dealing with any constants here. That means once you put this, some of you guys are thinking ahead of me. Once you put that x into here, you define an integral of x times the cosine, which means you have to use integration by parts. Bum, bum, bum. But if they give you an integration by parts, it's going to be easy. It's not going to be, it might be like this. This is, you shouldn't, I mean, if you're in Calc 3 at Steve, I think you should know that. But whatever. And you guys do. If you guys dig deep, I think you guys can get it. I have faith in you. All right, so let's just do the damn problem. All right. So f of x. The first thing we should do, something really easy, we should find b0, right? Have part of the answer already. So b0, that's a weird b. What am I, in second grade? b0. B, that's a nice bold b. b0 equals 1 over L, integral from 0 to L. What's L? Oh my God, I didn't write down L. 0 less than x less than 1. 0 less than equal to x equal to 1, or less than whatever, 1. Okay, this hair, it's not mine, is on here. Sorry. All right, so since we know what's L going to be, Joe Cuomo, what's L going to be? Good. All right, so 1, integral from 0 to 1. Integral from 0 to 1 of, the function x, dx. All right, integral of x squared over 2 plus c. We don't need the c because we have limits. 1, 0. So 0 is going to be 0, but we put in the 1, you get 1/2 equals b0. Or b naught, as some of the professors say. It's a 0. This is a naught. This is a 0. All right. So we got 1/2. That's good. Now, we need to find the other ones. We're going to do 3 non-zero terms. We'll do 3 not including this one. We'll find 3 other ones. Okay, so bn. Bn is going to be equal to 2 over L, which is just 2 over 1, because L equals 1. 0 to 1, because L equals 1. F of x, which is x, times the cosine of n pi x over L, which is just going to be 1. So we just leave it as n pi x. And of course, we got a dx in there. All right. So we got our old integration by parts right here, right? So, oh, there is. But what is L? 1. So yeah. So yeah, whatever. Over 1. Yeah. Okay. Integration by parts. I do it my tic-tac-toe method, magic trick, but I'm going to do it the real way so you guys know how to do it, just in case you forgot. Okay. So you got to do, what is it, UDV, ultraviolet voodoo, right? Is that it? UDV. There's a bunch of V's and U's and stuff, right? So you need a term you can integrate and a term you could derive out of these 2 parts. So this one you could derive. So this one is, well, you could do that for both, but pick one that derives to 0. By that I mean the derivative of this is 1, derivative of that is 0. So it goes down to 0. So this is going to be our u, right? This cosine term is going to be our dv. So I'm going to write that right here. So u equals x, du equals 1, because that's the derivative. dv equals cosine of n pi x. And then our v is going to be the integral of dv, which is going to be sine of n pi x over n pi, just like that. Okay, cool. So now, so now this is going to equal, bn's equal to, I think it's uv minus the integral of v du, right? Okay. So u is going to be x. V is going to be that thing. So sine n pi x over n pi minus the integral of v. So that's the same thing. So we could take out the, we don't take anything out yet. We'll leave it like that. All right, so sine of pi n pi x over n pi du, which is just 1. So this is dx. We have 1 dx. All right, cool. So we could do that. That's really, we could do that. Cool. All right. So once we take the integral of this again, and this is going from 0 to 1, and so is that. The whole thing's going from 0 to 1. But, OK. So once we have this, we can find the integral again. So it's going to be minus. I'm going to bring this part down. Leave this part here. I'm going to bring this down. And then I'm going to take all of it and bring it in the middle. OK. So it's the integral of this. You could have negative sine. So this turns into a plus. Or negative cosine, sorry. Cosine of n pi x. And since it's going to be another integral, it's going to be over another n pi. So you could just turn this n pi in the bottom into an n pi squared. Or n squared pi squared, however you want to write it. And this is going to be from 1, or from 0 to 1, just like that. All right. So now I'm going to bring it all, if you guys didn't see it because in the bottom, I'm bringing it all in the middle, and we're going to solve it for some constants. So Bn equals x sine of n pi x over n pi minus, or plus, cosine of n pi x over n squared pi squared from 0 to 1. OK. What? Yes. There is a 2 in front of everything. Good job, Jake. So let's put a 2 there. OK. So now we're going to solve this once we put in 1 and 0. All right. So if we put in 1, we get, stuff. Hold on. 2. Put in 1, this turns into a 1. Sine of n pi over n pi plus, still factor in that 2. 2, put in a 1 there. You get cosine of n pi over n squared pi squared. OK, plug in 0. Whole thing minus. Plug in 0 here. This whole term goes to 0, thank God, because I don't want to write 4 terms. So since that x is there, we plug in the 0 to the x, goes to 0. Good. Now we're going to plug in the 0 to here. So the cosine of 0 is going to be 1. So that means you are left with 1 over n squared pi squared. N squared pi squared. Just like that. All right. So now, what? 2. Thanks, Jake. All right. Any questions at this point? No? Yeah? Please ask questions if you're, like, lost. Yeah?
About the even odd thing. Like,
I think the B...
can you still, like, up in the very beginning,
Mhm.
can you still say that it's even though x cosine n pi x is odd? Can you still do that if it's odd? Plot x cosine n pi x is odd.
Well, another thing is, okay, because of the domain, we're assuming that we're dealing with 0 to 1. If this said negative 1, because L is the entire length of the thing.
There's an even extension on the opposite side of the...
Yes, yeah. But, I mean, like, even, like, yeah. Because we're only dealing with x from 0 to 1 also. So, okay. If they specify they put negative 1 to 1, then you're golden. Yeah. Yeah, we're gonna do it that way. So just to keep it consistent, we'll just find 2 terms with this because it's long. We'll find 2 terms with this. Find 3 non-zero. They might ask you for 4 or 5 on the test, but we'll do 3 here. So that means we're gonna find 2 terms with Bn, and this third term is gonna be with B0, which we already found to be what? 1/2. 1/2. All right. So now next step is the easy step. We're just gonna plug in values for n. So since we already have B0, we don't need to plug in 0. We plug in 1. So we plug in 1 to this. I'll put that right underneath. B1 equals, this is a lot of stuff, a lot of processing in your mind. All right, so 2 sine of pi. Sine of pi is 0. This thing goes away. Plug in 1 here. Cosine of pi is negative 1. So to be negative 2 over 1 squared pi squared. So negative 2 over pi squared. Minus 2 over n squared pi squared. So it's going to be minus 2 over pi squared. This is going to be negative 2 over pi squared minus another 2 over pi squared, which is going to be negative 4 over pi squared. Okay, that makes sense? I hear some chatter. Yep, question?
The 2 sine n pi over pi, can we just like cancel that out because n pi is always, like sine n pi is always going to be 0?
Yeah, we could. I'll leave it there, but yeah, we could. Yeah, okay. Yeah, good point. Yeah, because it's always going to be 0. If you put in any, so like for eigenvalues and everything, you put in anything n pi, sine of n pi, always going to be equal to 0 for any integer value. So that's a good thing too. Now, if you want to make it a little quicker for yourself. All right, B2. So we can plug in 2 to here. So that's going to be 0 because it's sine. 2 cosine of 2 pi. Cosine of 2 pi is going to be 1. So we have 2 over 4 pi squared minus 2 over 4 pi squared, which is going to be equal to 0. Great. We did another term. So now we're going to find B3. Same thing. So 3 sine, that goes away. If you put 3 into the sine, there's the integer value of sine. So now you have 3 pi, cosine of 3 pi is going to be negative 1. So we have negative 2 over 9 pi squared minus 2 over 9 pi squared. You can kind of see there's a pattern here. Negative 4 over 9 pi squared. So even from this, the next term would be negative 4 over, not 16, but 25, because you're going to skip one, because the even ones are going to, whatever. But that's if they ask you for like 6 or 7 terms. You could do that. OK, so now we have all the terms we need. We have 2 non-zero here, and you have B0. So we're going to write the answer. Answer is going to be f of x. So f of x is going to be equal to B0, which is 1/2, plus Bn. Bn is going to be, so you have B1 is negative 4 over pi squared cosine of n pi. So n is going to be what? 1. Pi x over L. L is 1. Yeah, the B2 doesn't count because it's 0. And then plus, or minus, sorry, minus 4 over 9 pi squared cosine. Since we're dealing n equals 3, so 3 pi x over 1. And that is your complete answer. Whoa. OK. We're done with that. Anybody have any questions? Marinate on that a little bit. Does that make a little bit of sense for now? You still have a lot of time to the final, so if it doesn't make complete sense, that's OK. All right, we good? I'll give you a minute to ask any questions, and then we're going to go. Let's take a minute break, because we're going to go on to partial differentials now. So it's going to get intense. It's going to be fun, though. That's the most important thing. We have to have fun, right? Right? All right. I don't like Fourier series at all. I hate it. But this stuff is, the PDEs are a lot of fun. OK. So I'm going to move this up, bring this third one down, so you guys can still see that. I'm going to erase this board, because we're going to need 2 boards, because this is, I'm going in on this one. And it's going to be intense. Does anybody have the time by any chance? Oh, we're in good shape. I said it was going to be short, but by short I meant like an hour and a half. But yeah, but after this one PDE, if you guys get it, if you guys feel like you want to go, you can go. Start on top. Yeah, OK. Well, yeah, I was going to do that. I was just erasing that one to get ready. Yeah. OK. All right. So it'll take me probably 20 minutes to write down the problem, because there's so many initial conditions and boundary conditions. All right. PDE. The question is this. So the final from the last 2 semesters had this good job, Jake. You're good at that. Okay, the final from the last 2 semesters had this exact setup, but they had different boundary conditions and initial conditions. So this is a good thing to know how to do. All right, you have a bunch of boundary conditions. BCs, boundary conditions. Ux of 0 comma t is equal to 0. And then ux of 4 t comma t is equal to 0 as well. And then we have our big initial condition, which is x0 equals cosine of pi x over 2 minus, bless you, cosine minus, bless you, 3 pi over 4 x plus 5 cosine. That's one condition, yes. I don't know. Okay. Ready to go. Ready to go. Who's ready for this? We're going to throw out the script. All right. All right, so you have all this stuff, right? You're going to get this on a test. You're going to be like, oh my God, this is it, right? So the first thing to do, take a deep breath. That's the first step of the problem. Take a deep breath. Next step, you have to set up what your answer is going to look like. That's a lot of diffq. You have to know what you're going to end up with in the end. So what you're going to end up with in the end, based on this. Everyone's like, what is this? It's a bunch of letters. There's only one number. This is math. There should be more than that. This is a function u that is in terms of 2 other functions, t and x. This t and x is capital T, capital X. And also there's lowercase t and lowercase x. Capital T is the function t of little t. So it's going to be big T of little t and big X of little x. Both of these functions are going to be multiplied together to come up with u. Our job, find both of those functions. And that's it. Then we celebrate. Okay. Oh, wait, midnight breakfast is tonight, right? That's good. I'm going to go to that. All right. I thought about that now. All right. All right. So like I just said, we need to, first step of getting the answers, to write down what it's going to look like. So u of xt is going to be equal to big X of x, big T of t. That's what it's going to look like. And from this step onwards, I'm just going to write big X and big T. I'm not going to keep writing the x of x and the t of t, because they get a little confusing. OK, next step is just like what is it? Undetermined coefficients. That's a good method. Just like that, we're going to find the derivatives of this that correspond to what you're given, and we're going to plug them in. So what you're given is u of ut. Wait, what? Oh, no. OK. OK. So u derivative of in the first derivative in terms of t, and the second derivative in terms of x. We're going to find both of those things of this and plug them in. And then we'll see where we get. We have a bunch of eigenvalues, a lot of fun. All right. So the first derivative in terms of t is simply, because it's just like doing partial derivatives. Whatever is not the derivative that you're taking it in terms of is just left constant. So your x is constant, and your t is just t prime. Right? You guys did this in the third test. I went over how to do this part, the separation of variables part. That's what this is. All right. So this is the u of t, ut. Now ux. Ux equals x prime t. Okay? Now we need a double derivative, second derivative, which is going to be uxx equals x double prime times t. Okay. Next step. Take these things, plug them in. So you plug them in, and you're going to get xt prime equals 3 times x double prime t. Okay. Good so far, right? Okay. We didn't really do anything yet, but all right. Next step gets insane right now. We need to separate these variables. But how we do so is critical. We need to have, first step is to make sure all of the higher, bless you, higher degree derivatives are in the numerator. So by that I mean your x double prime needs to be on the top, and your t single prime needs to be on the top. So we're going to separate these variables. We're going to put the x on the bottom here, and we're going to take the 3t, and we're going to put it down here. Because we want, if there's a constant, a 3, a 16, a 5, a k, a c, whatever it is, if there's a constant there, you want that constant to be with the lower degree because it's easier. If it's with the higher degree and you mess up or whatever, keep going. It's going to be a little tougher because you're going to have another number there, but you're going to get the right answer. But we want, to make it easier for ourselves, we want this 3t to be together with the single prime thing. That make sense? A little bit? OK. So you'll see what I mean. So now I'm going to actually stop talking and do something. All right. So do that, put that there, and then we'll take this t, move it over there, and the 3. So we end up with this. T prime over 3t. 3t equals x double prime over x. All right, we got that. So now, this is where it gets a little crazy. We're going to make this thing equal to negative lambda. Shit, that's something else. Why did we do that? I don't know. We just got to. It's a thing, right, Jake? It's a thing. So in DiffQ, we do this. Just memorize. That's what you do. Once you get to this point, make it equal to negative lambda all the time, or positive lambda. But I like negative lambda. Okay. There really is no preference. Like, it doesn't matter. Like, but I like negative lambda. That's the way I did it there, and I don't want to mess up. So OK. All right. So now, next step is to, you have these 3 things. This is equal to this is equal to this, right? We need to split this up to have 2 separate differential equations to solve. One of them is going to be by eigenvalue. The other one's going to be by not eigenvalue. I don't even know. It's first order, whatever, ordinary thing. OK. So first one is going to be, you have this thing. Let's focus on this right now. X double prime over x equals negative lambda. We can move this x over here, add this whole thing to here, and you end up with this. So I'll put equation 1. No, I'm not going to do that. Textbooks do that. It's weird. I'm getting a call from one of my friends from home that I don't really care about.
So you don't watch this YouTube video.
Yeah, you didn't watch this YouTube video and unfriend me on Facebook. All right, so all right, I shouldn't have said that. All right, let's focus on the DiffQ. We got this. We got this. We got x double prime plus lambda x equals 0. Everyone makes sense, everybody? Good? All right, cool. All right, so now we're going to do the same thing with the t prime over 3t equals negative lambda. Move this 3t over here, add everything over. T prime plus 3 lambda t equals 0. All right, good. So we have a second order and a first order. So here's a second order with a lambda. What do we do? Eigen. Boom. Hit nail on the head. All right. So this thing, we're going to find eigen. So do eigen. All right, do eigen. Take that as you will. So, yeah. All right, so case 1. Actually, no, we're not going to do cases yet. Turn this thing into r's. That's what we first do. So we'll take this thing up here. Good. R squared plus lambda equals 0. Not lambda r, because this is just x, not x prime. So r squared plus lambda equals 0. So now r squared equals negative lambda. R equals plus or minus square, OK, whatever. Yeah, that's right, right? Yeah. Negative lambda. OK, plus or minus square root of negative lambda. All right. It would have been, I think I should have used positive lambda, but I'm in too deep, man. All right. So once you have this, we could do case 1, case 2, and case 3. And we're going to find our values. And it's going to be a good time. All right. So next step, case 1. I'll go through this one a little fast because case 1 is nothing usually happens. I've actually never seen anything happen with case 1. All right. I'll stop talking. The negative lambda, whatever's underneath the square root, you could have a negative lambda plus 2, minus 2, whatever it is. Whatever's underneath the square root, set it greater than 0. So if that's the case, that means negative lambda is going to be equal to a squared, where a cannot equal 0. So we have negative lambda equals a squared. Plug this a squared back into r. This means that r equals plus or minus a. All right, r equals plus or minus a, which means we know what the homogeneous looks like. So this would be x homogeneous equals C1 e to the ax plus C2 e to the negative ax. All right, so now we're like, okay, we need to have our initial conditions. That's what we would normally do with eigenvalues, right? So where are our initial conditions? This says initial condition, but that's not, we're not using that, no. For the eigenvalues, this is important because some people don't know which one's which. For the eigenvalues, you use your boundary conditions. For your later, when we have things that look like cosines and sines, which is complex, not to give it away, but I just did. That is going to be later. That's going to be our initial conditions. Boundary conditions are used for the eigenvalues. So we have, what this means is that the first derivative in x, so x prime, is going to be when x is 0 and t is just t. We don't ignore t. It's going to be when this is going to be equal to 0 when x is 0. And similarly, the derivative when x is 4 is going to be equal to 0 as well. So this is what x looks like right now. So to use any of those boundary conditions, we first need to find the derivative. This might not always be the case. You might have one where it's just u of 0, t equals 0. But here, both of them in terms of the first derivative in x. So we need to find the first derivative in x. So x homogeneous prime equals a c1 e to the ax minus a c2. I don't know why I wrote a period. c2 e to the negative ax. Okay, so now we have the derivative. We need to plug in both of our values. Our first one's going to be 0, not 4. 0. So we plug in 0, and we get all the e's cancel out. You get a c1 minus a c2 equals 0. So right off the bat, this means that c1 is equal to c2. All right, cool. So now, I'll move this up a little bit, like that. There we go. All right. So now we could say that x homogeneous prime of 4, we can write that down as a c1 e to the 4x minus a c2 e to the negative 4a, sorry. Wait, yeah, okay, 4a. Cool. All right, so we have this. That makes sense? Okay. We just plugged in the 4, 0, and then we found out this relationship. Now we're plugging in the 4. This equals 0. Okay, since we know that C1 and C2 are equal to each other, we can just get rid of the C2, put it into C1. Okay, and then we could do a little magic trick. Take this equals 0, goes away. Put an equal sign right there. Right? That's crazy. So after that little magic trick, we can see that the A's cancel out, the C1s cancel out, and is that true? No. E to the 4a does not equal e to the negative 4a. There's no value of a that makes that true. So from this, you can tell that nothing, it just doesn't work. So you put nah, doesn't work. Doesn't work. Okay, that makes one person laugh. Okay. Okay, so now we're done with case 1, the easiest case of all. Now we're going to move on to case 2. Now case 2, don't take it for granted. I'll go on the bottom here. We have room. Okay, so case 2. Don't take it for granted because sometimes you might end up with an arbitrary constant value, eigenvalue and eigenfunction for case 2. But we're not going to use it to carry through. So let's see what we got for this one. We have case 2 is when everything underneath the square root is equal to 0. So we have negative lambda is equal to 0. And that's easy. You just plug it in. So r equals 0. And if r equals 0, our x homogeneous is going to be c1 plus c2t. Because it's 0 and it's one real root. So you have the c1 e to the alpha t plus c2t e to the alpha t. Alpha is 0. Oh my God. That's like normally I'd be like, oh, x is t is whatever. That's important for this one because we have both. All right. So x homogeneous. Now just similarly, to use these boundary conditions, we need to find a derivative. So let's do that. So x homogeneous prime equals c2. That's it, c2. All right. So if that's the case, from the first one, when you plug in 4 or when you plug in 0, or you plug in 4, it equals 0. So we know that c2 equals 0 at all times from that. But that's okay. That's great, right? So that means this doesn't exist. What we have left is x homogeneous equals c1. Now there's nothing explicitly said about c1 based on these two boundary conditions because they're both in terms of the first derivative in x. Sometimes a lot of times when you see both in terms of the same thing, whether it be the zero derivative, the first derivative, second derivative, then most of the time you're going to end up with an arbitrary value for your case 2 eigenvalue. So that's what we have here. We have, that makes sense to everybody? We have an arbitrary value. So now we have C2 equals 0. Nothing was explicitly said about C1. So if that's the case, that means we have that. We have XH, or X homogeneous equals C1, or just any arbitrary constant, Cn. Okay, so that is the eigen function, because it's a function of X. So this is one answer. Now, we're not going to carry this answer through when we deal with this. We're only going to carry the case 3 answer through, because that actually has meaning. All right, so with every eigen function, there's an eigenvalue. So the eigenvalue for this would be what? We look up here, case 2, what are the parameters of case 2? Negative lambda is equal to 0. So move the negative, whatever, get rid of it. Lambda is equal to 0. So lambda equals 0. So this is your eigenfunction, eigenvalue, boom. Now we're going to move on to case 3. That's when I use the other board. Okay. Does that make sense so far through case 2? Yeah? All right. Yep. Nothing. You just circle it and say, this is an eigenvalue, and then you move on. and you say, you can just say, like, you write like fancy words, arbitrary constant value, function, number. You just write down something that sounds cool. All right. So now, case 3. This is important. So case 3 is when everything underneath the square root, which is negative lambda, is less than 0. That means negative lambda is equal to negative a squared. Okay. So now we're going to plug this into R. R equals plus or minus the square root of negative a squared, which is equal to plus or minus ai. Boom, boom, boom. Here comes our complex. Right? Yeah, well, get used to it. And I think Calc 4 has this too. So I never took it, but it has it. Because Chem Bio is only going to take that. But I'm lucky. Okay. So we have plus or minus ai. So with this plus or minus ai, we can find our homogeneous with complex, which a lot of us know how to do. Here's a little refresher. So x homogeneous. Since we don't have an alpha, anything in front of the plus or minus, we're just going to have C1 cosine of ax plus C2 sine of ax. Boom, we have that. All right, so now we are going to do the exact same thing as we've been doing. We're going to use our boundary conditions, which are x of 0 and x of 4. So let's use x of 0. Oh, we find derivative, right? Ooh, yeah, derivative. So x homogeneous prime equals derivative of cosine, negative sine. So negative C1a sine of ax plus C2a cosine of ax. Okay. So now, next step is to plug in our boundary conditions. So x homogeneous of 0 equals, sine of 0 is always 0. Cosine of 0 is 1. C2a equals 0. From that, a cannot be equal to 0. I'll write that down. That's always a thing. So that means C2 is equal to 0. So that means we got that out of the way. We don't have to worry about C2. So now we're only going to worry about this, or this one. Using our next boundary condition, which is the homogeneous derivative of 4 is equal to 0. We're going to ignore the C2 part and just end up with negative C2a sine of 4a. Oh, yeah, I'm dumb. Sorry. C1. Okay, C1a sine of 4a equals 0. All right. So now we have to go through this whole thing. Can C1 equal 0? No, because then the whole problem would collapse on itself. Can a equal 0? No, because I said it. Can sine equal 0? Yes, it can. That's what has to be equal to 0 for this to work. So, like I said, I think I said it when we were doing a Fourier series, what values of sine make it 0? Any integer multiple of pi, whether it be 0 pi, 1 pi, 2 pi, everything that's flat in the unit circle, the sine is 0. So we need to make whatever is inside the sine equal to that n pi value. So we literally could just write that. We write 4a equals n pi. So whatever's inside the sign equal to n pi. If this is true, that means the sign is always equal to 0. Okay, cool. Any questions on that? No? Okay, cool. Okay, so now this is true. What we need to find, what our goal right now is to find the eigenvalue and then later the eigenfunction. So the eigenvalue can be found by lambda. So what do we have here? We have lambda in terms of a. From this, we need to find a, because that makes sense, because if we find a, that means we can find lambda. So we can move this 4 over. Move over the 4. You have a equals n pi over 4. Okay, so if that's the case, I'm going to do a little magic trick. Watch this. So a equals that. So I'm going to write this. I'm going to write equals negative lambda. So we have that negative a squared equals negative lambda. Watch this. Negative squared. Negative squared. Wow, right? It's crazy. So that equals the same thing. So now this whole thing works out. Does that make sense to everybody? Okay, cool. So this whole thing works out. This equals negative lambda. But we want positive lambda. So you just get rid of the negatives. So you have n pi over 4, whole thing squared, equals lambda. And it equals lambda n. So I'm going to box that. That is our lambda value. That is our eigenvalue. That's good. So now we need to find our eigenfunction. There's a common mistake right here, where people, instead of going to the original function, they go to the derivative. Because we've been dealing with the derivative for so long with the boundary conditions, people stay here and try to put this lambda back into here, or put the a back into here. But we need to put the a back into here to find what our actual eigenfunction is. So that is going to be xn equals, since we have c2 equals 0, we can ignore this whole part. So you have c1, which is just going to be cn, cosine, that's not a cosine, it's just a co, cosine of ax. So what is a? A was, so since we have 4a was equal to n pi, a was equal to n pi over 4. So write that in here, n pi over 4 x. And that's it. This is our eigenfunction. So what we did from all of that work, we found 1/2 of the answer. But the second half is much easier. Yeah, we're almost done. So if you get this, you'll get 70% right, 70% of the points. So we found x, maybe even less. I don't know. They grade hard, so I don't know. Yeah. So we got x is that. Any questions on that? On the whole eigen process, case 1, case 2, or case 3, or anything in between? No? You guys good? All right. Good. I'm glad you're with me. All right. So then the next step, now this is going to be stuff that's not eigen-related. It's going to be a little, maybe you haven't seen it before. Okay. So the next step is the other equation that we're dealing with, that we're trying to find, is our t. From this equation, I'm not tall enough. That one. So we have t prime plus 3 lambda t equals 0. All right. Oh, God. You just dropped a bunch of papers. All right. So we have, so he just dropped all of his classes everywhere. Yes. All right. So t prime, since we're only having this, since this t equation is a first order equation, that means since it's first order, we're going to have how many constants? 1. So we can solve this. We have lambda. This lambda, we're going to use this value. But I don't want to plug it in right yet because it'll look a little sloppy. So we're going to go as far as we can with this until we need to plug in lambda. So with this, we can do the exact same thing. Turn it into r's. Turn to r's. Mike r's. We turn them r's. OK, plus. That was tacky. All right. So we r plus 3 lambda equals 0. So if that's the case, r equals negative 3 lambda. All right. So now since this is a first order, you can solve first order like this, by the way. I try to solve this. This is a linear. It looks like linear. I try to solve this linear. It doesn't work because there's a 0 here. Because you need to multiply the mu of x by 0. Whatever. I'll go over that stuff tomorrow, when the first exam stuff. All right. So you have this r. So the t homogeneous, the t equation, is going to be equal to a constant, a different constant. I'll write a, or an, because we're dealing with stuff. All right. So an e to the negative 3 lambda t, or little t. And then we only have one term because, I'll write A1 for now. All right, we only have one term because this is a first order equation. So does that make sense for everybody? Because this is, you haven't explicitly solved first order in this method, but it's pretty easy. But I mean, if you have any clarification questions. No? Okay. All right, good. I don't know if you're like just dozing off or you actually understand. I hope you understand it. Okay. Okay. You guys are smart. You got it. All right. So now once we have t, we have lambda in here. So we're going to take this lambda and we're going to plug in the lambda that we found doing this whole crazy eigen process. So t is going to equal to a. So now we're plugging in lambda. Lambda is in terms of n's. So we can make this t, tn. This a is going to be an. E to the negative 3 times n pi over 4 squared. Like that. And then we're going to have a t next to it. So that's going to be our tn. So that's a t equation. All right. So now we have our t equation. We have our x equation. Right? That's all we needed, right? We need to have our u equals x times t. But maybe some of you are just wondering, what about that big initial condition? What do we do with that? Here's what we do with it. We need to match it up with x. All right. So right now, our answer looks like this: x times t, which is going to be, and by the way, once you multiply these two, you have cn cosine whatever, and an. These two constants multiply together just equal another constant. So we can turn this c and a. We'll turn that into, I don't know. We can leave it as a c. We'll leave it as a c. Make it simple. So we have u of xt is equal to cn cosine n pi over 4x times e negative 3 n pi over 4 squared times t. All right, so that's our, now you have 80% of the points of the problem. So that's good. Okay. Next step. Next step is we need to look at our initial condition. Actually, that's good because you can't see it otherwise. All right. So initial condition all the way up there is that u of x comma 0. That means when x is just x and t is 0. So for this to work, and no derivatives, thank God. I'm not taking a derivative of that. And you won't get any derivatives. So once, so now x is just going to be x and t is going to be equal to 0. Once t is equal to 0 here, this whole e term goes away. So that's good. That means this happens. So u x of 0 equals cn cosine of n pi x over 4. This has to equal all of that stuff. So I'm going to rewrite it. Cosine pi x over 2 minus 7 cosine of what? Jake, you tell me.
3 pi over 4x.
Pi over 4x, and then what's the other one?
5 cosine.
Uh-huh.
3 pi x over 2.
3 pi x over 2. All right, it's plus, right? Yep. Okay, cool. So obviously this one term can't equal these three terms, but if we have three different n values, they can. Oh, snap is right. We need to set this up so that these n's match with this n, and it just matches. So here's what we're going to do. We're going to take this term by term. We're taking this template of what each term is going to be, and we're going to try to find n. We're going to try to find our cn, and then we're going to put them all in. All right, so looking at the first one, comparing. We need to both compare them and be a little smart here. So looking at the inside of the cosine, we have pi x over 2. Here you have pi x over 4. What can you multiply? What can you put in for n to make this equal to this? 2. I heard 2. Good. If n equals 2, that makes this 1/2 pi x. 1/2 pi x. Okay, so for this, n equals 2. So that means if n equals 2 for this term, that means this is the n equals 2 term, right? So if that's the case, that means c2 equals whatever's in front of the cosine, which is 1. So that means we have c2 equals 1. All right, next one. What about this one? Oh, that's an m. N equals, so you have 3 pi x over 4 and n pi x over 4. N's going to equal 3. So n equals 3. All right, so if n equals 3, that means we have this value, negative 7, is going to be our C3. C3 equals negative 7. Next one, so we have n equals 3 pi over 2, n pi over 4. So we have 6, because we want 3 over 2. If you simplify 6 over 4, it's 3 over 2. So we want our n equals to 6. It doesn't always go like 3, 4, 5 or whatever. Just take it term by term. So if n equals 6, that means C6 is equal to whatever is in front of the cosine, which is 5. All right, so that we got everything. We're basically done. Now we just plug everything in, right? It's exciting, right? Remember, it's exciting. It's exciting. It is. All right, so we got all that stuff. Now, let's write this answer. U of x, t. Now we bring the t back. We could just, well, we could put it in the front. E. Actually, wait. You can't put it in the front. With this n, so, OK. Let's just write stuff. All right. So you have, the first one is C2 equals 1. So you have 1 cosine of pi x over 2. Pi x over 2. And then you have, the t. Well, you see the n there's an n in the t equation also, right? E to the negative 3 n pi or whatever squared. So this n corresponds to this n. So n equals 2 here. So e to the, this would be negative 3, 2 over 4 pi and then squared. So this would be 1/2. So it would be pi over 2 squared t. Like that. So that makes sense for the first term. Kinda? All right. You guys ask me questions later. OK. Minus our C3 is going to be equal to negative 7. So it would be plus 7 or plus negative 7 or just minus 7. N is going to equal 3. This cosine term stays the same. So cosine of 3 pi over 4x. And then you have e to the negative 3. So it's going to be n pi over 3. Since n equals 3, it's going to be 3 pi over 4 squared t. And then our last term is going to be plus 5 cosine 3 pi over 2x e to the negative 3. Since n is equal to 6 here, 6 over 4 pi and the whole thing squared, which is going to be 3 over 2 pi squared t. And bada bing, bada boom, this is your entire answer. All right, that's it. Is there any questions now? I will take questions. Yeah. All right. If you feel like this is enough for now, you can leave. But I'm gonna go over one more. I'm gonna go over one more. Question. Yeah. Oh, yeah. You did that. That was on the WebAssign, right? Or I think, right? That was what I think it was on the WebAssign. I think they're gonna be like this. It's been like this for years. Even last semester, even when they changed the class, these were always the same. So yeah. Same kind of thing. The only thing, the difference between heat and wave equation is what derivatives this is. So like, I think the wave equation is, or whichever one this one isn't. Okay. No, the wave is like when they're both double derivatives, right? Something like that. I'm gonna go over one now where they're both double derivatives. So you have UTT and then UXX. Yeah. All right. So I'll. What? Oh, I'll put the notes on Facebook or whatever. Yeah. Thanks for coming. Joe, how do you feel? All right? Exam 3? Wait, there was no exam. Well, exam 4 is the final. You mean, I'm going to do tomorrow is going to be exam 1. I'm not going to do exam 3. I'm going to do exam 2 on Friday. But exam 3, because I did exam 3 review like recently, kind of recently. So that stuff's kind of fresh. But I mean, I was thinking about it. I might. Yeah, it'll be a last minute decision.
Is it like on like exam 3 that you did before? Is it on SITTV?
No, I don't think so. No. But yeah, this is the first time I saw it. So yeah, interesting. They called me up. They're like, hey, you want to be on? I'm like, sure, or whatever. All right, cool. I'm glad you learned something. All right, I'm glad. Hey.
Do you know if there's this shit? It's like the eigen, not eigen. It's the initial value. This goes IVK. Because I never really gave a shit
Let's
for
see.
this before,
Yeah.
like right now.
Let's see.
But
What's your solution?
because there's like not much work there, and they don't really put all.
This is the same thing.
Is this the same thing?
Yeah, you just do it.
You just do it. Okay.
Oh, this is part D. This is part D of like the rest of the problem.
Oh, that
Yeah.
makes sense.
Yeah,
Oh,
the rest
is
of
that what
they.
we just did?
Yeah, we did the entire thing. That was just part D.
I think I'm gonna have another part.
Okay. All right, so this one I'll go through a little faster. I'm not going to talk as much, 'cause I'm sure you guys don't want to hear me talk. Where is it? Okay. Yo. I don't know. Ask him. Is this going on YouTube later? When? Okay, yeah, so. School content, ooh. Yeah, I didn't even do this one, so it might be iffy. I don't know. I got it. Yes, this is what it is. Yeah. I don't know. I'll figure it out. I'll let you know. All right, so I am doing this now. Whatever this is. All right, this is the next problem. So the one I just did was, I think, I don't know, heat wave, or one of the heat or wave things. I don't know which one. And this one is the opposite of that, the heat wave, whichever one it wasn't, because it's different because you have UXX and you have UTT here. Okay, so I'll let you guys write that down. They'll just give us the math. They'll give you the math. They might say a bunch of complicated words and then give you this. They're like, give us the eigen, and then write this. Yeah. They write, they write like part D, use this, blah, 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 find the terms of the, blah, blah, and it's just this, like, same thing. So we're going to use the same exact method. Since there's like two double derivatives, they give us another initial condition, which we're going to use to do that. I didn't even do this problem yet, so I don't know. We'll figure it out. I don't even know if it works. We'll figure it out. No, it works. It works. I'm putting some mystery in it, so you guys pay attention. It might not work. But I don't know. It might not work. I don't know. It looks like it looks weird. I don't know. Okay. So I'm going to get to it. First step, same thing. U is in product of two functions, x and t. So we make u equal x, t. All right. I'm going to just go. I'm just going to go. So then we need to plug in the derivative. So uxx is equal to x double prime times t. And then utt is equal to x t double prime. Just like that. So now we're going to plug in those for our initial function, which is going to be uxx, which is going to be x double prime t minus 16 x t double prime. This whole thing's going to equal 0. All right, so now when you make these two things equal to each other, and we can separate variables. So this goes away, make this equal, the little magic trick. So now we're going to put this, now they're both second order, so the 16 can go anywhere. But like preferably keep it with a lower degree thing, so it's like, so it's not like, so you don't end up with doing an eigenvalue of like 16x double prime, because then you have like 16r squared. You don't want to deal with that. So the way we're going to separate this is we're going to have x double prime divided by 16x. Actually, no, I don't want to do that. Actually, I have to. Yeah. No, I don't. But I don't want to. Okay. Okay. Okay, so now we're going to do 16t double prime over t, and that's going to equal lambda, or negative lambda. I don't know. We'll do negative lambda. Okay. Makes sense so far? Same. We did the exact same thing. We're leaving the 16 up here with the t's. We'll figure it out when we get there. I don't know what's going to happen, but whatever. Okay. So now we need to make these two equations, the x equation and the t equation. So let's make the x equation. So x is going to equal so x double prime. Move this x over here, add it to the other side, add it back. So you have lambda x equals 0. And then the other one's going to be 16t double prime plus lambda t equals 0. All right, so we have that. So now, or you could even like divide the 16 out and do lambda over 16, t equals 0, but whatever. We'll cross that bridge when we get there. Okay, so now we're going to have, we'll use this, we'll find the eigenvalues of this. So x double prime plus lambda x equals 0. I'll write down eigen. All right, eigen. So now we're going to have r squared, return to our r's, r squared plus lambda equals 0. R equals plus or minus square root of negative lambda. Just exactly the same as we did before. All right. Am I going too fast? No? Okay, cool. All right, so now after this, we could use case 1. I'll write case 1 right here. So case 1 occurs when everything underneath the square root is less than 0. I mean, no, that's wrong. Greater than 0. Good, greater than 0. So now that's greater than 0. We're going to turn negative lambda equal to a squared, right? Can't equal 0. R is going to equal plus or minus a, because once we plug in this a squared to here, square root of a squared is just a, and it's always going to be plus or minus, because that's what square roots do. So r equals plus or minus a. X homogeneous equals c1e to the ax plus c2e to the negative ax. Just like that. All right, so now we're going to use our boundary conditions. So similarly to before, where we had our x equals 0 and x equals 4, both equal to 0, we have 0 and then 1. But the good thing is we don't have two derivatives. We just have no derivative and then the first derivative. So we could, right off the bat, once we find this homogeneous, we can plug in 0 for x. So let's do this. So once we plug in 0 for x, I'll write that right underneath. X homogeneous of 0 equals c1 plus c2 equals 0. So from this, we can have the relationship that c1 equals negative c2. Everything's all fine and dandy. All right, so once we have that, we can find the derivative of y homogeneous, y prime homogeneous, and you have c1, I don't know what that was, c1a e to the ax minus c2a e to the negative ax. And this, once you plug in 1, is going to be equal to 0. So let's plug in 1. So you have c1 a to the e a minus c2 a to the negative, or e to the negative a equals 0. All right, so now from that, we can take away the 0, make that equal. So now we have the relationship that c1 equals negative c2. So you kind of can see what's going to happen here. I get it, you can see what's going to happen here. So you have negative c1, just like that. So the c1s cancel out. So you're left with negative a equals that. So the a's cancel out as well. And you're left with that, which that's never true again. So e to the a can never equal negative e to the negative a. It's just not It's not the same thing. And then from this, you can tell it doesn't work. So no. All right. Any questions on that, on case 1? Pretty straightforward. You guys should be experts at case 1. Okay. So now case 2. Case 2 is when everything underneath the square root is equal to 0. In other words, r is equal to 0. If r is equal to 0, that means our x homogeneous is going to be equal to c1 plus c2t. I did that before too. X. C2x. All right, so once you have that, same exact thing. Oh, I'm getting old. Okay, same exact thing. Plug in your initial conditions. So initial condition, you have 0 and then 1. I was looking at that up there. Yeah, ignore that stuff. That's from last problem. So you have 0 and then 1. So you plug in 0 to this. Of 0 equals c1 equals 0. Because then if you plug in 0 to here, this goes away. c1 equals 0. So we have that. That's true. So now we find the derivative, x homogeneous prime, which equals c2. So it just equals c2. And this is going to plug in 1 to a constant. It's just going to be 1. And that's going to equal 0 as well. So there you have explicit proof, unlike the other problem that we did, that c1 and c2 both equal 0. So that's really important. That means that case 2 doesn't work either. There's no arbitrary constant, whatever values. It's just c1 and c2 equals 0. All right, any questions on that? No? Okay, good. All right, so now big bad case 3. I think we could fit it on this board actually. So let's try it. So case 3. So for case 3, negative lambda is going to be less than 0. So that means that negative lambda is going to be equal to negative a squared. Same exact thing as before. So eigenvalues and PDEs, this whole main process, exact same thing. So you guys get down eigenvalues first. You can bang this out, no problem. This should take you like 5 minutes. All right, so well, once you get good at it, it's a lot of practice. But once you get to Tuesday, you guys should be good. Okay, so negative lambda equals all that stuff. So now we have r. We just cut right to the chase. R is going to equal plus or minus ai. Because you're going to plug in this negative a squared into here. And you're going to get, since it's a complex root, so you're going to have plus or minus ai. All right, so that's good. Yeah, so now with plus or minus ai, we know what the homogeneous is going to look like. So x homogeneous equals c1 cosine of ax plus c2 sine of ax. All right, cool. So now we can plug in the first initial condition already, which is 0, 0, 0, basically. So h of 0 equals cosine of 0 is 1. Sine of 0 is 0. So now from this, we know that c1 is equal to 0. So that's good. So now we can take the derivative of this. And we're going to plug in the other term. Am I going too fast? No? Cool. All right. So we're plugging in the find the derivative first. So find the derivative of this. The derivative of cosine is negative sine. So we're going to have negative c1a sine of ax. And then the derivative of sine is cosine. So you have c2a cosine of ax. All right, so now once we plug in 1, which we could simply do by getting rid of the x, because x is just 1, we can make this equal to 0. Now, since we already know that c1 is equal to 0, this whole term can go away. So you're simply just left with c2a cosine of a equals 0. Okay, so once we know that c2 can't equal 0 because c1 already is, and if that was the case, that means this wouldn't work. A can't equal 0 because why? I said so, or I should say so. A not equal 0. Oh, it's a cool alpha. I didn't even try to draw that. All right, A cannot equal 0. So cosine of A has to be equal to 0 then. So sine, when we have sine equal to 0, we want the sine to be inside the sine. We want a integer multiple of pi. So 1 pi, 2 pi, 3 pi. When it's cosine, we want, or when it's cosine 0, it's at the top of the unit circle, bottom, and that's represented by an odd multiple of pi over 2. So like 1 pi over 2, 3 pi over 2, 5 pi over 2, etc. So that's represented by making this inside thing of the, whatever's inside the cosine, whether it be a pi, whatever it is, a is equal to 2n plus 1 times pi over 2. Now, sometimes there's 2n minus 1. That works, but only if you have to start n from 1 instead of 0. I like starting n from 0 because that's like, I don't know, I like it. So we have a now. Everyone understand how I found a? By making the inside of the cosine equal to 0 by this, an odd multiple of pi over 2. So now this is a. That's good. So this is a. We can just do this. We can make this negative, square it, put everything in parentheses, negative, or I'll make that clearer, negative, and then square it. This equals now negative a squared. What does negative a squared equal? Negative lambda equals negative lambda. So we get rid of the negatives, and I'm going to go up here. We have lambda n is now equal to 2n plus 1 times pi over 2, the whole thing squared. Okay, so that is our eigenvalue. Any questions on that? No, we good? All right, cool. So now we're going to do our eigenfunction. Now we can't go to the derivative. We have to go to the original function. So our eigenfunction is going to be xn equals, what do we have equals 0? C1 is equal to 0, so we're just dealing with the C2 term. That's going to be Cn sine of a. A is equal to just 2n plus 1 pi over 2. 2n plus 1 pi over 2 times x. And that's it. So this is that is our x. So we found x already. Next thing we need to do is find t. So I'm going to switch boards. I'm going to move this one up and take this one, erase this one, take this one down. Yeah, this is the old problem, right? Yeah. Oh, yeah, cool. All right. Make sense so far? You can ask any questions when I'm erasing or whatever. Or just sit there. Whatever. What time is it? 7:30. Okay. Thanks for staying, by the way. There's something to do. Yeah.
For the case 2,
Mm-hmm.
the x nine, is that because the cn, the arbitrary c again?
Oh, no, because we know for a fact that C1 and C2 equal 0. Before, we had C2 equals 0, and then nothing said about C1. Okay. Like, oh, see, yeah, I didn't erase that part. Oh, yeah, so that's equals 0. So we had, yeah, we had that. I erased everything else, but we had that. Yeah, okay. Okay. So now we have, what do we have? We have x. So we have lambda. We have lambda equals, I'm going to rewrite lambda, is 2n plus 1 pi over 2 squared. Okay. So now we have our t equation. So 16 t double prime plus lambda t equals 0. And we have x. So x equal, I'll try to write down what we have so we don't have to keep referring to over there. Cn sine 2n plus 1 pi over 2x. All right, so now you can kind of see already, if you like stop here and look ahead, see that kind of matches up with this. So you can already see that, oh, this Cn is going to be negative 6 and you have 13. So all we need to do, we have that part on lockdown now. So all we need to do is find our equation for t, which, I don't know, I'll figure it out. So we have we have this condition that the first derivative when t is equal to 0 is 0. So we could let's just see what happens. So 16 r squared plus lambda. We have lambda, but I don't feel like writing this whole thing in yet. I'm going to write it in at the end. So we have plus lambda equals 0. Okay, so now we could we could divide by 16. I want to do that. Divide by 16, that equals 0 still. So we have r squared plus lambda over 16 equals 0. Question? No? Okay. Okay, so we have r now r squared equals negative lambda over 16. So the square root of that is going to be r, plus or minus. Okay. So now, we already know, oh, okay, I see what's going on here. I know what to do. All right. All right, we have lambda. Let's plug in lambda now. Let's see what happens. So we have, put a big square root. Okay, so we plug in lambda. We have negative lambda here. So why do we have negative lambda there? Okay, we have negative lambda. So we have 2n plus 1 pi over 2. Whole thing's going to be squared. It's going to be a negative sign over 16. Okay. This is crazy. Anybody have any ideas? This negative is throwing me off. So, okay, what I'm getting at here is, all right, so we could just make this complex. We could take this out and square root everything. So if we, okay, so we leave the negative there, right? So this is basically negative 1 times the entire thing. This is just something squared over 4 squared. If we square root everything, that's the same as square root in the top and square root in the bottom, because we're dealing with division and multiplication. So we can rewrite this as 2n plus 1 pi over 2, that whole thing, because you're square rooting the square, over 4i. Yes. Plus or minus. All right, so you're left with that. Does that make sense? I know it's getting a little tricky, but does that make sense? Okay, I hope it does. Okay, plus or minus. So now with this is an I. So that means complex again, so complex root. So I'm gonna call this, what should I call it? Well, give me something. Sigma. No. Phi. Okay. Okay. So we'll call it phi, right? Because I don't want to keep rewriting this like 5 times. Okay, so now we have a complex root. So that means we need to do t homogeneous, again, equal. We don't need to do it on a whole eigenvalue because we know what it is, or we know what lambda is already. So t homogeneous is equal to c1 cosine of phi t plus c2 sine of phi t. Okay, so now we have a condition. We have the derivative is when t is equal to 0 is equal to 0. So let's find the derivative. See, that's why I want to make it a phi. So I'm going to have to take the derivative and rewrite this 5 times. So t homogeneous prime is equal to negative phi c1 sine of phi t plus phi c2 cosine of phi t. All right, we got that. So now t homogeneous prime, we know that when you plug in 0 to t, it's going to equal 0. Plug in 0 here, the sine term goes away. First term goes away. You plug in 0 to second term, you have cosine is equal to 1. So you have phi c2 is equal to 0. Now the whole phi term, which is this, if you plug in n equals 1, 2, 3, 4, 5, this is never going to be equal to 0. So, and even if you plug in 0, it's not going to be equal to 0. It's going to be equal to something. So this is never going to be equal to 0, but c2 is. That's what this means. So now we have c2 is equal to 0. That means this term we can get rid of. We don't care about this term at all. So now that means this is our answer. So this is gone. Oh, wow, I actually figured it out. Huh, okay. Pat myself. All right, so once you have c2 equals 0, this whole c2 term is gone. That means we're left with this. Little modification, this is our answer for t. So I'm going to write Tn equals Cn times the cosine. I'm not going to write phi this time. I'm going to put everything in. Of 2n plus 1 pi over 2 over 4 times t. And that's it. So this is our Tn. That makes sense? Pretty much. Yeah, it's kind of a more complicated and more involved than the other one, but if you follow through with it and you like have willpower, you're gonna get the right answer. I know that sounds silly, but like a lot of this takes like grit and willpower to just like keep going through it, because you might be tired. You might be like, what time is your test? 8 a.m. Right? Yeah, it's probably 8 a.m. Okay. Yeah, it took me. I mean, not to freak you out, it took me 3.5 hours to do, but I'm not. They'll be like, oh my God, he's really smart. If he took him 3.5 hours. No, I went really slow. I did every problem like really like slow and thorough. I did my work. I worked hard too. So don't rush. If you see someone getting out in an hour and a half, don't think, oh my God, they're so smart. What do I do? Think, okay, they quit. And no, don't quit. All right, they tapped out. All right, so now we have t. Let's get back on track here. So now we have t, we have x. Once t is equal to 0, look what we have, a cosine, right? If t is equal to 0 in this cosine equation, you're ending up with this whole thing being 1, right? So if we multiply these two together, right now, here's what we have. I'm going to rewrite what we have right now. So u, our whole complete answer, is equal to these two x and t multiplied together. If you multiply x and t, x has a constant, cn, and t, I also made it cn. It should be an or whatever. Multiply those two constants together, what do you get? Another constant. So we're going to call it cn, doesn't matter. And then you have our x term, which is going to be sine of 2n plus 1 pi over 2 x. Now we have our t, which is going to be cosine of, bless you, cosine of bless you. Over that, over 4, t. All right, this is our complete answer, what we have right now, without putting in any of the initial conditions with the terms, with those two sine terms that look so deadly. All right, so now we're going to do that. All right, so once, just like the other one, that initial condition says that t is equal to 0. So if t is equal to 0 here, this whole term becomes 1, and we don't have to worry about it for this. So I'm going to rewrite that initial condition right here. So negative 6, all right, initial condition. So negative 6 sine, what does it say, 3 pi over 2x? Yeah, 3 pi over 2x plus 13 sine 11 pi x over 2, just like that. All right. So now we're going to try to make this work. So looking at what's inside this sine, question? Yeah. Yes, we did that already. The second initial condition, you mean? Yeah, we did that already here when we were trying to find out what t was. Okay. All right. No, it's all right. Good question, though. Good to clarify stuff. All right. So now we're trying to find out, just to do the same thing we did for the last problem. We're trying to make this look like this. The inside of this sine look like the inside of this sine. So what value of 2, or what value of n does that? Looks like 1, right? Because we want a 3 in front of here, 3 in front of the pi. If you put in 1 right there, this becomes 2 times 1 plus 1, which is 3. So for this we have n equals 1. If n equals 1, that means whatever is in front of the sine, which is negative 6, is going to be our what? Our c1. So that means c1 equals negative 6. Our second term, you know whatever it is, c whatever is an equal 13. But here we have 11. So what gives us 11? 5, right? So if n equals 5, you have 10 plus 11. So if n equals 5, that means c5 is what this corresponds to. c5 equals whatever's in front of the sine, which is 13. Okay, does that make any sense? That makes sense? All right, good, good. I like it. All right, so once we have that, we're basically done. So I'm going to rewrite the entire answer. I'm going to erase this. If it's okay if I erase this in the middle, yeah, I'm going to do it anyway. All right. So rewrite the answer. So we have u of xt equals. We need to have our this term, these terms, this term, and this term. So this term we have -6 sine of 3 pi over 2x. Now we need to add our t, our like t function, which is this part, right? So this part, this is still part of the first term. So in the first term, n equals 1. So we need to put that same n equals 1 into here. So that means we have cosine of 3 pi over 2 over 2, that whole thing over 4 times t. You could turn this into an over 8. Just like that. Second term. That's why I only gave you 2 terms, because it's kind of long. Second term, we have 13, which is our C5, times the sine of 11 pi x over 2, times our cosine term from our t function, which is going to be cosine of C5, n is equal to 5. We put in 5 there. 11 pi over 8, because we have over 2 over 4, which is going to be over 8. We can simplify, and that's it. That is our answer. You get 100. You put that. All right. Any questions at all? And if not, that's it. So I'm going to put I'll put some notes. I'll put these notes on Facebook, actually. I'll just like post them on to SITTV group, or I don't know. Post them on SITTV group in 2018. I guess I'll do that. Okay. That's it. Yeah.
Fourier series.
Okay.